Hello students, in today's lecture we are going to solve NCERT exercise problem on mechanical properties of fluids. This is our disclaimer. Learning objective. By the end of this lecture you will be able to solve questions on mechanical properties of fluids by applying concepts of hydrostatic pressure, surface tension and equation of continuity using proper reasoning and calculations. So in today's lecture, we will cover NCERT exercise problems, mechanical properties of fluids. There are total 20 questions in this exercise. But we are going to cover only 9 questions, 9.1 to 9.9. 9.1. Explain why. A. The blood pressure in humans is greater at the feet than at the brain. B. Atmospheric pressure at a height of about 6 km decreases to nearly half of its value at the sea level, though the height of the atmosphere is more than 100 km. And C. Hydrostatic pressure is a scalar quantity even though pressure is force divided by area. So we will see answer of each part one by one. So let's see the solution. The pressure of a liquid is given by the relation, and that relation is P equal to H rho G, where P is the pressure, H height of the liquid column, rho density of the liquid, G acceleration due to gravity. Alright. Now, first, or we can say A, we have discussed about blood pressure. So blood pressure is greater at the feet than at the brain in humans. It can be inferred that pressure is directly proportional to height. Hence, the blood pressure in human vessels depend on the height of the blood column in the body. The higher the column, the more weight it has, and the greater the pressure at the bottom. This is just like how water pressure is higher at the bottom of a swimming pool than at the top. The height of the blood column is more at the feet than it is at the brain. This means the pressure from the weight of the blood is higher at the feet. Hence, the blood pressure at the feet is more than at the brain. This is why doctors sometimes measure blood pressure at the arm, which is about halfway up the body to get a standard reading. It's all about how the height of the fluid column affects the pressure. Alright. Now, let's start with part B of the question. The density of air is higher near sea level. This means that the air is packed more closely together at the bottom of the atmosphere, which affects how pressure changes as we go up. So density of air decreases with increase in height from the surface. At a height of about 6 km, density decreases to nearly half of its value at the sea level. So at a height of about 6 km, density decreases to the nearly half of its value of the sea level. Atmospheric pressure is proportional to density. So hence at a height of 6 km from the surface, it decreases to nearly half of its value at the sea level. Even though atmospheric goes up to 100 kilometers, most of the air and therefore most of the pressure is concentrated in the lowest few kilometers. All right. Now, let's focus on part C. When force is applied on a liquid, the pressure in the liquid is transmitted in all directions. Hence, uh, you know, because hydrostatic pressure acts equally in every direction and does not have a single fixed direction, we call it a scalar quantity. No, scalar have a only magnitude, not direction, unlike vectors. So even though pressure is calculated as force divided by area in fluids, it's the same in all directions at a given depth. 9.2. Explain why. A. The angle of contact of mercury with glass is obtuse, while that of water with glass is acute. B. Water on a clean glass surface tends to spread out, while mercury on the same surface tends to form drops. C. Surface tension of a liquid is independent of the area of the surface. And D. Water with detergent dissolved in it should have small angles of contact. And E. A drop of liquid under no external forces is always spherical in shape. Let's see the solution. So first, let's define angle of contact. This is the angle formed between the tangent to the surface, to the liquid surface at the point where the liquid, solid and air meet. Here in the figure, you can see the angle of contact, often labeled as theta. The tangent is drawn at the point where the liquid touches the solid surface. This angle tells us whether a liquid will wet the surface or not. For example, water on glass has a small angle of contact, while mercury on glass has a large obtuse angle. SLA, SA, and SSL are the respective interfacial tensions between the liquid air, and solid liquid interfaces. Now, at the line of in contact, the surface forces between the three media must be in equilibrium. All right. At this contact line, the forces from the surface of the solid, liquid, and air must balance each other. This balance of surface forces is what determines the angle at which the liquid meets the solid surface. So the formula cos theta equal to SSA minus SSL divided by SSL. The angle of contact theta is obtuse if SA less than SLA, as in the case of mercury on glass. And this angle is acute if SSL less than SLA, as in the case of water on the glass. All right. Now, B part. Let's start with mercury. Mercury molecules are strongly attracted to each other, but not very attracted to glass. This strong internal attraction causes mercury to pull itself together, forming drops instead of spreading out. That's why the angle of contact between mercury and glass is obtuse, meaning the drop sits up high on the surface. On the other hand, water molecules make acute angles with glass. All right, which means the drop flattens out more. This is because water molecules are more attached to the glass than to each other, so they tend to cling to the surface. They have a weak force of attraction between themselves and a strong force of attraction towards solids. Hence, they tend to spread out. Now, C. Let's start with part C. Surface tension is defined as the force acting per unit length at the interface between a liquid and another phase. This means for any given length, along the surface, the liquid molecules experience a pulling force that tries to minimize the surface area. Remember, the SI unit for force is Newton, and for length is its meter. So surface tension is measured in Newton per meter. This force is independent of the area of the liquid surface. Hence, surface tension is also independent of the area of the liquid surface. Now, let's start. Uh, let's examine part D. So, water with detergent dissolved in it has a small angle of contact. The angle of contact is the angle where a liquid surface meets a solid surface. A small angle means the liquid spreads out more on the surface, which is important for cleaning because it helps the water and detergent reach more areas of the fabric. This is because for small theta, there is a fast capillary rise of the detergent in the cloth. The capillary rise of a liquid it is directly proportional to the cosine angle of contact angle theta. If theta is small, then cos theta will be large, and the rise of the detergent water in the cloth will be fast. All right. Now, let's start with part E. A solid tends to acquire the minimum surface area because of the presence of surface tension. The surface area of a sphere is the minimum for a given volume. Hence, under no external forces, liquid drops always take a spherical shape. Fill in the blanks using the words from the list appended with each statement. A. Surface tension of liquids generally with temperature increases or decreases. B. Viscosity of gases with temperature, whereas viscosity of liquids with temperature or increases or decreases. So arrange respectively. C. For solids with elastic modulus of rigidity, the shearing force is proportional to, while for fluids it is proportional to shearing strain divided by rate of strain. D. For a fluid in a steady flow, the increase in flow speed at a constriction follows conservation of mass or Bernoulli's principle. For the model of a plane in a wind tunnel, turbulence occurs at a dash speed turbulence for an actual plane, greater or small. So here you have to find out the uh, answer of dash. Let's see the solution. A. Answer is decreases. Surface tension of liquids generally decreases as temperature increases. This means that as you heat up a liquid, the molecules moves faster and the attractive forces at the surface becomes weaker. So the surface tension drops. For example, warm water has less surface tension than cold water. The surface tension of liquid is inversely proportional to temperature. All right. Now, let's focus on part B of the question. The answer is increases, then decreases. This means that the viscosity of gases increase with temperature, while viscosity of liquids decrease with temperature. All right. Most fluids offer resistance to their their motion. This is like internal mechanical friction known as viscosity. Viscosity of gases increases with temperature, while viscosity of liquids decreases with temperature. Now, C. Let's focus on part C. For solids, the shearing force is proportional to the shearing strain, while for fluids, it's proportional to the rate of shearing strain. Shear strain is how much a material is deformed by a force, and the rate of shear strain is how quickly that deformation happens over time. This difference is key to understanding why solids and fluids behave differently under stress. With reference to the elastic modulus of rigidity, for solids, the shearing force is proportional to shearing strain. With reference to elastic modulus of rigidity, for fluids, the shearing force is proportional to the rate of shearing strain. Alright, now D. Conservation of mass and Bernoulli's principle. For a steady flowing fluid, an increase in its flow speed at a constriction follows the conservation of mass or Bernoulli's principle. So, Bernoulli's principle is based on the conservation of energy for flowing fluids. When a fluid moves through a constriction, its velocity increases to maintain the same flow rate, and as a result, the pressure drops. For example, if the water flows through a garden hose and you pinch the end, the water comes out faster, but with less pressure inside the hose at that point. All right. Now, last answer is greater. For the model of a plane in a wind tunnel, turbulence occurs at a greater speed than it does for an actual plane. This follows from Bernoulli's principle, and different Reynolds numbers are associated with the motions of the two planes. Alright. Explain why. A. To keep a pipe of paper horizontal, you should blow over or not under it. B. When we try to close a water tap with our fingers, fast jets of water gush through the openings between our fingers. C. The size of the needle of a syringe controls flow rate better than the thumb pressure exerted by a doctor while administering an injection. D. A fluid flowing out of a small hole in a vessel results in a backward thrust on the vessel. E. A spinning cricket ball in air does not follow a parabolic trajectory. Alright, let's see the solution. When air is blown under a paper, the velocity of air is greater under the paper than it is above it. As per Bernoulli's principle, atmospheric pressure reduces under the paper. This principle is fundamental in fluid mechanics and helps explain many phenomena every day. This makes the paper fall. So, to keep a piece of paper horizontal, one should blow over it. This increases the velocity of air above the paper. As per Bernoulli's principle, atmospheric pressure reduces above the paper and the paper remains horizontal. This is a direct application of Bernoulli's principle. Higher velocity means lower pressure. Alright. Now, B. So, let's focus on part B. According to equation of continuity, area into velocity equal to constant. For a smaller opening, the velocity of flow of a fluid is greater than it is when the opening is bigger. When we try to close a tap of water with our fingers, fast jets of water gush through the opening between our fingers. This small openings forces the water to move faster as it exits, creating those fast jets. This is because very small openings are left for the water to flow out of the pipe. Hence, area and velocity are inversely proportional to each other. Alright. Now, let's start with part C. The small opening of a syringe needle controls the velocity of the blood flowing out. This is because of the equation of continuity. At this constriction point of the syringe system, the flow rate suddenly increases to a high value for a constant thumb pressure applied. When a fluid flows out from a small hole in a vessel, the vessel receives a backward thrust. A fluid flowing out from a small hole has a large velocity according to the equation of continuity. So area into velocity equal to constant. Now, uh, according to law of conservation of momentum, the vessel attains a backward velocity because there are no external forces acting on the system. All right. Now we will focus on part E. So a spinning cricket ball has two simultaneous motions, rotatory and linear. These two types of motion opposite the effect of each other. When the ball spins, it can actually slow down the air flowing underneath it. This happens because of rotation of the ball opposes the direction of the air flow on the bottom side. Remember, slower air means higher pressure according to Bernoulli's principle. Hence, the pressure on the upper side of the ball becomes lesser than that on the lower side. An upward force acts upon the ball. So, as a result, the ball follows a curved path instead of a simple straight or parabolic one. This upward force from a Magnus effect bends the ball's trajectory, making it curve in the air. This is why bowlers can make the ball swing or spin in cricket. It does not follow a parabolic path, right? A spinning cricket ball does not follow a parabolic path because the combination of spin and forward motion creates a pressure difference, resulting in a curved trajectory. This is a great example of how fluid mechanics and real world sports are connected. 9.5. A 50 kg girl wearing high heel shoes balances on a single heel. The heel is circular with a diameter 1.0 centimeter. What is the pressure exerted by the heel on the horizontal floor? Now, let's see the solution. So, let's start by listing what information we have. Mass of the girl 50 kg. Diameter of the heel d equal to 1 centimeter. And here we need to convert it in meter. So, it will be 0.01 meter. Radius of the heel r equal to d by 2 is equal to 0.005 meter. Alright. Now, area of the heel a equal to pi r square. So put the value and a equal to pi into 0.005 whole square. So solving this, you will be get the area, which is 7.85 into 10 raised to the power minus 5 meter square. Force exerted by the heel on the floor, that is F equal to mg. So substitute the value 50 into 9.8, so 490 Newton. Alright. Now, pressure exerted by the heel on the floor, so it will be force upon area. So just substitute the value 490 divided by 7.85 into 10 raised to the power minus 5. So solving this, you will be get 6.24 into 10 raised to the power 6 Newton per meter square. Therefore, the pressure exerted by the heel on the horizontal floor is 6.24 into 10 raised to the power 6 Newton per meter square. Torricelli's barometer used mercury. Pascal duplicated it using French wine of density 984 kg per meter cube. Determine the height of the wine column for normal atmospheric pressure. Let's see the solution. The density of the mercury ρ1 equal to 13.6 into 10 raised to the power 3 kg per meter cube. Height of the mercury column H1 equal to 0.76 meter. Density of French wine ρ2 equal to 984 kg per meter cube. Height of the French wine column that is equal to H2. Acceleration due to gravity 9.8 meter per second square. Alright. Now, Pressure in both columns is equal to pressure in the mercury column is equal to pressure in the French fine column. So rho 1 H1G equal to rho 2 H2G. So H2 equal to rho 1 H1 divided by rho 2. So substitute the value. You will be get H2 equal to 10.5 meter. Hence the height of the French vine column for normal atmospheric pressure is 10.5 meter. Alright. A vertical offshore structure is built to withstand a maximum stress of 10 raised to the power 9 Pascal. Is the structure suitable for putting up on the top of an oil well in the ocean? Take a depth of the ocean to be roughly 3 km and ignore ocean currents. Let's see the solution. So answer is yes. Structure suitable for putting up on the top of an oil well in the ocean. The maximum allowable stress for the structure is 10 raised to the power 9 Pascal. Depth of the ocean is 3 into 10 raised to the power 3 meter. And density of the water 10 raised to the power 3 kilogram per meter cube. Acceleration due to gravity 9.8 meter per second square. Alright. Now, first let's recall how to calculate the pressure exerted by the fluid at a certain depth. So we know the formula P equal to rho dg. So just substitute the values and solve it. You will get 2.94 into 10 raised to the power 7 Pascal. The maximum allowable stress for the structure is 10 raised to the power 9 Pascal. That is greater than the pressure of the seawater. That is 2.94 into 10 raised to the power 7 Pascal. Pressure exerted by the ocean is less than the pressure that the structure can withstand. Hence, the structure is suitable for putting up on top of an oil well in the ocean. A hydraulic automobile lift is designed to lift cars with a maximum mass of 3000 kg. The area of cross section of the piston carrying the load is 425 centimeters square. What maximum pressure would the smaller piston have to bear? Let's see the solution. So let's first identify the maximum mass of the lift is designed to the handle. So here the maximum mass of a car that can be lifted m equal to 3000 kg. Area of cross section of the load carrying piston A equal to 425 into 10 raised to the power minus 4 meter square. The maximum force exerted by the load F equal to mg. So let's substitute the values and solve it. You will be get 29400 Newton. Alright. So the maximum pressure exerted on the load carrying piston P equal to F by A. So P equal to 29400 divided by 425 into 10 raised to the power minus 4. So solving this, you will get 6.917 into 10 raised to the power 5 Pascal. Pressure is transmitted equally in all directions in liquid. So that therefore the maximum pressure that the smaller piston would have to be bear is 6.917 into 10 raised to the power 5 Pascal. A U-tube contains water and methylated spirit separated by mercury. The mercury columns in the two arms are in level with 10.0 cm of water in one arm and 12.5 cm of spirit in the other. What is the specific gravity of spirit? Let's see the solution. The given system of water, mercury and methylated spirit is shown as follows. So here the height of the spirit column is 12.5 cm. In meter it will be 0.125 meter. Alright. So always remember to use SI units in calculations to keep things consistent and avoid mistakes. Alright. So here the pressure at this column is P naught and in this column is also P naught. Alright. And spirit is 12.5 centimeter AB and CD water is 10 centimeter. Now, the height of the water column is given as 10 centimeter, which we convert to meters for SI units. So 10 centimeter equal to 0.1 meters. Always remember to use standard units in calculations to avoid mistakes. So P naught is equal to atmospheric pressure and rho 1 is equal to density of spirit. Rho 2 equal to density of water. Alright. Now here this is U2. So pressure at the point B is equal to P naught plus H1 rho 1 G. Alright, the pressure here is the atmospheric pressure P naught plus the pressure due to the water column above it. So we write pressure B equal to P naught plus H1 rho 1 G. Alright, pressure at point D is equal to P naught plus H2 rho 2 G. So uh, now let's visualize the setup for with this diagram. The U2 one arms contains water above mercury and the other has methylized spirit above mercury. The mercury acts as a barrier between two liquids. Pay attention to heights 10 centimeter of water and 12.5 centimeter of spirit. This pictures help us see how the fluids are arranged and where we all compare the pressures. So pressure at point B and D is same. So P naught plus H1 rho 1 G equal to P naught plus H2 rho 2 G. So rho 1 upon rho 2 equal to H2 upon H1. Now solving for specific gravity. So rho 1 upon rho 2 equal to 10 upon 12.5. So it will be 0.8. So the density of spirit is 0.8 times density of water. This value 0.8 is the specific gravity of the spirit. Alright. So this is the answer. Thank you for your attention. I hope this lesson was helpful.